So, welcome everybody who's joining us this morning, this afternoon, depending on whereabouts you're located with us. This is our Antarctica Week Festival, the first day of our festival. It's the second of 10 talks we have going on this week. And so we hope that you'll enjoy them. And if you're unable to join all of them during the week, they will be available as recorded talks on the Thwaites Glacier website a day or so after each of the live sessions. We have Julia Wellner with us this afternoon or this morning from the University of Houston, who's going to give us a talk on the footprint of past ice. And you may have seen from her bio with the registration that she's an assistant professor at the University of Houston and a lead principal investigator on the Thor project, which is part of the International Thwaites Glacier Collaboration Program. And she and her team investigate sediments deposited in the seas near the Thwaites Glacier and reconstruct past changes in environmental conditions and the glacier's response, adding to context the projections of future change. I'm sure she can probably explain things a little bit better than I can. So today, the format of the session is Julia's going to give us a talk for about 30 minutes, and then we'll have a Q&A session afterwards. So if you do have a question, there should be a Q&A function at the bottom of your screen that you can type in a question for us. Some questions we have received beforehand at the point of registration. We'll also go through those if we can, but unfortunately we may not be able to get through all questions. Try and answer as many as possible. And please do remember to put either your school's name or perhaps where you're located or where you're watching us from today. And we may be able to just give you a shout out and understand how many people are watching us and where from. So with doing that, I'll hand you over to Julia.
Okay, good morning, everybody. I see that people are still logging in through that introduction. I know sometimes it takes a little while to get through the waiting room on Zoom. So welcome, everybody. Good morning from Houston. And I'm happy to share some of our work on Thwaites Glacier with you. So I am going to start with a video that was produced about the area we are studying. Should take about 5 minutes, and then we're going to go to my talk. And Sarah, you just interrupt me if the video doesn't play properly, but I think it's all set up. So welcome, and I'll talk to you again in 5 minutes.
Sea level rise will be one of the greatest challenges we face in the next century. How high seas rise and how soon has a lot to do with what happens here. Antarctica holds the largest chunk of ice on Earth. Its western portion alone contains enough ice to raise sea levels by more than 3 meters. And it's in big trouble, largely because of this, the Thwaites Glacier. Its face towers as high as a 6-story building and extends for 120 kilometers across the coast of West Antarctica, making it about the size of Florida. It's a humongous glacier that reaches right into the heart of West Antarctica. And that's a major problem, because in the past couple decades, it's become increasingly clear the Thwaites Glacier is falling apart.
These are portraits of a vast, rugged, treacherous continent which has challenged man since first he could sail beyond the limits of his horizon. Antarctica.
This is the Antarctic ice sheet. It's thickest in the middle, where years and years of snowfall compacts into ice. As the middle builds, it pushes ice out towards the oceans via glaciers. And the part of a glacier that floats on water is its ice shelf. Today, man-made climate change is warming the air and water around Antarctica, causing each side of the ice sheet to melt, but at very different speeds. The eastern ice sheet lies mostly on high ground, above sea level, which keeps it relatively safe from warm ocean water. That means it's melting slowly and remains relatively stable. But West Antarctica is different. Most of it lies below sea level. That means as it thins, water can undermine it, possibly kickstarting a more rapid collapse. It's why West Antarctica is considered the most important piece of ice in the world when it comes to climate change. Here's another view of the bedrock underneath Antarctica's ice sheet. The green, yellow, and red parts are land above sea level, like in East Antarctica. But these blue areas in West Antarctica are all below sea level. This area, where the bedrock slopes continuously for more than a mile down and deep into the center of Antarctica, is the Thwaites Glacier. And it could be the most dangerous glacier in the world.
Surrounded by 3 mighty oceans, the seas are as much a part of Antarctica as her highest mountains.
Right now, Thwaites is barely hanging on. In the past 30 years, the front of Thwaites' ice shelf has lost a lot of ice, causing it to retreat backwards. With a smaller ice shelf to slow the flow of ice, the flow of the glacier speeds up. But the bigger problem is the glacier's grounding line, the final point where the glacier rests on the bedrock. That grounding line has been shifting backwards as warm ocean water reaches underneath the ice shelf. It's moved 14 kilometers since 1992. So ice that used to be on land becomes ice that is floating on water, raising sea levels. The downhill slope of the bedrock means that as the grounding line moves back, it lifts an even bigger slice of ice behind it off the land and into the water, and that accelerates the flow of the glacier into the sea. The amount of ice flowing from Thwaites has doubled over the past 30 years and already contributes 4% to global sea level rise. And scientists have recently detected a huge cavity, 2/3 the size of Manhattan, down here. Scientists believe this could mean Thwaites' collapse is inevitable. How soon that happens is hotly debated.
The sleeping continent is awakening, slowly at first, but with ever-gathering momentum.
The complete collapse of Thwaites will take centuries, and it's affected by many different things, from the temperature of the ocean currents to the makeup of the bedrock. But research shows that humans can possibly slow or even stall its collapse by curbing greenhouse gas emissions soon. That's important because some scientists believe collapse could start this century, while others say it's already underway. The collapse of Thwaites would add about 0.5 meter of sea level rise and trigger a much bigger catastrophe. Because Thwaites reaches into the middle of West Antarctica, its collapse could cause the rest of the ice sheet to collapse with it, resulting in more than 3 meters of sea level rise in the next few centuries. That would submerge not only Miami and southern Bangladesh, but also parts of the Netherlands and New York City. So while there's a lot of uncertainty around Thwaites, one thing is clear. Once it starts to collapse, it won't stop.
Okay, so hopefully that was easy for you to see and hear. And now, Sarah, you should be seeing my PowerPoint. Again, interrupt me if you do not.
Nope.
So, okay, good. So I love that video. It's got such great graphics explaining what we do and what Thwaites is doing today. What I'm going to talk to you about today is just a little bit of how we study Thwaites' past, and we call this the footprint of past ice. And what we mean by footprint is where the ice used to be. And the reason we study where the ice used to be is in part because we are interested in what it's going to do in the future. But scientists have only been studying Antarctica and the ice sheet there for a few decades. And that's not enough change for us to fully understand how the ice will behave in the future. And therefore, scientists like me and my colleagues and our students study how the ice behaved in the past so that we can see a little bit longer history and understand more about what it might be in the future. So that video showed you our current understanding, and I'll show you just a little bit more about how we look at the past. And again, my name's Julia. I'm on the faculty at the University of Houston, and I'm part of the International Thwaites Glacier Collaboration. Most geology and Thwaites and glaciology talks don't have any penguins, and I think everyone's disappointed when there are no penguins in an Antarctic talk. So there they are, and we'll keep going. This is an image of Antarctica in the middle. You guys can all see that. And so the South Pole is in the middle of this image. And as you just learned in that video, we have the West Antarctic on this side and the East Antarctic on the other side. The West Antarctic is smaller and has a much smaller ice sheet. The East Antarctic on the other side is much larger and with a thicker ice sheet. Even though the West Antarctic ice sheet is smaller, it is the one that we are the most interested in because of its potential for change. All of these colored lines that you see over this image are ship tracks. showing where the US Antarctic program, because that's what I work on the most, the US Antarctic program has sent ships in recent decades. And what you can see in the red line is the US icebreaker, the Nathaniel Palmer, that's the ship I work on, and we're going to show you in a minute, has gone back and forth along West Antarctica. These blue lines up here are cruises from the smaller vessel that's not as strong and can't make it as far south. But what you see is that for decades, we have been focusing our efforts on West Antarctica. Yes, it's easier to get to. Even, East Antarctica is farther away, harder to get to. But this is the one that's changing. And so we keep going back over and over to try to study that. Yellow is my own personal cruise tracks back and forth. So my 11 seasons back and forth along that coastline. And I show you this as a reminder that while Thwaites is big news right now and changing and important, we have known for decades that West Antarctica was susceptible to change and something we needed to study. So why do we study it all? Well, sea level rise is the reason. If all of ice melted on the planet, sea level might rise on the order of about 65 meters. Many of the world's large population centers would be flooded. It would not look like this cartoon. It would not be this dramatic sudden tidal wave, but rather the millimeter by millimeter, centimeter by centimeter that we are seeing each year already. So this 65 meters is some number that's way off in the future, and a number that's much more than we have to worry about in foreseeable centuries. It's the ultimate number. But what counts is the bit by bit by bit that we're already seeing. So where is all of that ice stored? Well, a lot of the world's ice is in Antarctica. And so this is an image showing Antarctica, and hopefully you're starting to recognize its shape. Here is East Antarctica, here is West Antarctica, the South Pole in the middle. There's the peninsula pointing off towards South America, Chile and Argentina. And so the Antarctic is about the size of the United States and Mexico combined. So most of that ice then is stored in Antarctica, and it's thick. So I'm going to show you some cross sections, just like the ones you saw in the video, so that you can understand how thick the Antarctic ice sheet is. So we're going to look at two slices, like a cake slice through Antarctica. We're going to look from the South Pole out to the edge in East Antarctica. And we're going to look at a slice through West Antarctica as well. So remember, this is all the size of, a couple large countries. And we're going to slice through it and look at the ice on top of it. So East Antarctica, that goes from the South Pole out to the ocean, is largely above sea level. And like you saw in the video, that means that the ice is largely sitting up on bedrock on the continent, and therefore is not in contact much with the ocean. And if the ocean rises or warms, it won't affect this ice. It's out there on the edge, it won't be bothered. On the other hand, West Antarctica, shown here in this upper cross section, the ice is actually largely sitting in the ocean. That means that it's responsive to changes in the ocean. So the West Antarctic ice sheet is sitting largely underneath sea level, and it's sitting down deep into the ocean in some places. It has a floating tongue in many places. This is called an ice shelf. And this floating tongue also helps control how the ice behind it behaves. So we've got a warm ocean out here, at least warmer than ice. It's not frozen, therefore it's above freezing. So this liquid water is sitting in contact with this ice. So if that water raises or warms, it's going to affect what the ice does adjacent to it. So to summarize what I just said and what the video said, the West Antarctic ice sheet and the peninsula are grounded below sea level. They're sitting down deep in the ocean. They're foredeepened. That means once it starts to retreat, it will keep retreating. And many areas have ice shelves. And as you saw in Thwaites, that ice shelf has already broken away largely. And so that the grounded ice is almost reaching the ocean. So here's just another cartoon now with a ship added, so you can start to understand what we do to study the past behavior. So if ice is retreating, the places that are currently ocean used to be ice. And so we as marine scientists can work in the ocean and study where the ice used to be. So now I'm going to take you into our project. And again, I am working on a project called Thor, which stands for Thwaites Offshore Research. And we are part of the International Thwaites Glacier Collaboration, which is funded through the US and the UK science programs. So here we have Pine Island Glacier and Thwaites Glacier. And this is part of West Antarctica over here. And this is East Antarctica on the other side. So far, every time I've shown you an image, Antarctica has been oriented like this. South Pole in the middle, 0 degrees longitude on the top, 180 degrees longitude on the bottom, the peninsula sticking up here towards the left. So this way would be towards South America. This way would be towards New Zealand and Australia. This is the traditional way to show Antarctica when you're showing the whole continent, right? So you see the whole continent with the South Pole in the middle. But if you've ever been working with maps, you've probably been taught to put north on the top of your map. That doesn't work in an image like this because we have to project north out in each direction away from the pole. But now I'm going to start to show you some images over here of Thwaites Glacier. So we're going to rotate the image around and show you Thwaites Glacier with the ocean normally on the top of the map, because that's the north when we zoom in, and Thwaites, the continent and the ice, normally on the bottom of the image, like you would in class normally. So what does Thor do? Thor is, again, the Thwaites Offshore Research Program. We are studying where the ice used to be. And so this cartoon is supposed to show you everything we're doing. We have ice flow back here. This is the grounded ice. Here is this floating ice that's coming out over the ocean. Here is the ship that we are using to study it. And this ocean out here is where we're going to study the footprint of the ice, where the ice used to be. So this ice has been shrinking and shrinking and shrinking and shrinking. So when we are far out on the left side of this image, we are in the oldest part of the record. And as we get closer and closer and closer to where the ice is today, we are getting to more and more recent parts of the record. That means that we can use distance as a way to study time. So if we're interested in what happened in the past, you can't necessarily go into any one place and get that history. On the other hand, we're going to use place as a proxy or a record of time. So a couple pretty pictures. This is the Nathaniel B. Palmer icebreaker. This is a drone photo taken this year. We had a field season January to March, coming home in early April this year, 2020. And this is a drone image of the Nathaniel Palmer icebreaker taken in the Amundsen Sea near Thwaites and Pine Island glaciers. So this is the Thor research team and some of our colleagues at sea. Some of our students are shown here. And in the back, sort of looking down, this is the drone pilot taking our picture. What you can see is a very typical picture of what an icebreaker should look like. Icebreakers often have these big wings up here, large windows in all directions, so that you can see out in 360 degrees and look for icebergs and sea ice as we are working. We do work very close to Thwaites Glacier, and that means lots of times we are working in ice, like at least this thick. You also see it's not all that cold. Yes, it's around freezing, but we're all perfectly happy to be out there in the sun for a little bit. Not super, super cold. Here's another drone photo taken a few days earlier than that one. This is actually near Pine Island Glacier, and you can see the glacier in the back. This is all attached ice in the background. Here is a large iceberg that recently broke off and calved and will float away. Here is the ship that we work on. It's 300 feet long. Here's a little tiny bit of ice. And you can see that it's largely open water. This is good for our work. It's much easier to do our science when we have open water. And here, this little path actually is of the lifeboat. So this drone photo was taken during the monthly lifeboat test. So you see the little scale of our lifeboats and the big ship we work on. So what I'm going to do now is show you a little bit of our data and how we work offshore of the ice to study where it used to be. This little spaghetti mess, pink spaghetti all over the place, is the cruise track we have this year. And like I said, you're looking at ocean on the top of the image, land and ice on the bottom of the image. So north is on top and south is on the bottom, just like a proper map is supposed to be. What you see though is that there's a lot of floating ice out here in this satellite image. And in gray here, you actually see the bathymetry, the depth of the ocean as we're working. This spaghetti mess of a cruise track is because we are constantly responding to where sea ice is, to where ocean conditions are, and to what's changing around us. Doing marine science in the Antarctic, just like any other science in the Antarctic, we have to be responsive to the weather and to the harsh demands of the continent around us. And that means that the ship, we are usually having to go to plan B or plan C or plan D in order to keep working. So this is where we study. This is Thwaites down here. This is the ocean. And this is Pine Island down here. So what do? We do a variety of things, including geophysics and geology. This is an image of some of our multi-beam bathymetry data, where you see in black is ocean, in white is ice, either attached to shore or out here floating. And in the colors are data we have collected to look at how deep the ocean is. If you're working in the Gulf of Mexico or the North Sea, maybe finding out how deep the ocean is not that big of a deal. You know, there's 1,000 boats that have been there before, and many people are already fully aware of how that ocean has been mapped. But in the Antarctic, one, there have hardly been any ships. Most of the places we work, there's only one ship a year at most. And that means that just basic information like how deep is the ocean is not yet known. So not a lot of people have been there. More interesting kind of is that the amount of ocean to survey is growing each year because that ice is retreating, because the ice is stepping back and getting smaller and smaller and smaller. There's more and more ocean for us to go study each year. That's a bad thing overall for climate change. But as a marine scientist, it is a burgeoning business to be in there. So we study how deep the water is, and that lets us map where the ice used to be. We do other types of geophysics, meaning we look into the subsurface and we can see where there is bedrock in some places, or where there is sand and mud and other types of sediment building up like a mud pile at the bottom of the ocean. And so we do types of geophysics so that we can see the bottom and understand what's down there beyond just the depth, but what sort of bottom, hard or soft. And then we go in and we take cores. So this is probably the closest thing that you think of as geology. And I'm going to show you a couple examples now of cores, how we come in and we study the geology in this area. So again, here is the ice down here at the bottom of the image. So north is on the top. Out here is ocean. In the colors is where we have measured the depth. Blue is deep, deep water. Yellow is shallower water. White is places we didn't make it to. We have to go back. And I'm going to show you a couple examples of spots where we go in and take cores so that we see that sand or mud that's down there. Here are photos of what we do at sea, so what our field work is like. We take a variety of types of cores, from the very short, just about a ½ meter, to the pretty long, 6 meters, sometimes 12 or 15 meters long. So different types of cores are collected. We work at sea. This is one of the Thor team members collecting the mud and the water over it that we've just retrieved. So this isn't necessarily always the most glamorous work. We lay down on the deck of the ship, end up covered in mud, covered in water, sometimes at around freezing temperatures. But those records are then brought indoors to the lab, like is shown in this lower left figure. And those cores then are opened and studied in the lab. So again, here's some pictures of Thor colleagues looking at this mud that is brought in. In this case, this is the bottom of the core down here where the students are working. The top of the core is up here. And so again, using not this time distance, but using depth as a proxy for time, we can know that the top of the core is giving us the most recent record. And as we go down, 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 farther down the core, we're getting farther and farther back in time. That allows us to tell how the ice was behaving in the past. So we can map how far it was and study how it changed over time. So I'm going to hustle through an example for those of you that want the detail. If we're working close to the grounding line, so in this top picture right here, close to the grounding line, where the ice is in contact with the bed and the ocean, then we get sediments that are really sandy and cobbly and gravelly, and everything's poorly sorted and everything's in there all jumbled up together. Or you can move far out to the ocean, and if we take one of those cores out there in the ocean, then it's much finer grained, it's muddy and silty instead of gravel. A lot of the material that's in it is actually marine organisms that have lived and died and fallen into the sediment. There's nothing living down here. So we can find very different cores if we're out in the ocean versus close to the grounding line. And in the middle, you get the middle. So for one example taken right here in this shallow area just north of the ice edge, so very close to where the ice is, in a shallow bank, we've taken a core, and at the very bottom of that core, we find that coarse, gravelly, poorly sorted sediment with everything jumbled up in it. And as you move up through the core, it gets a little bit finer. It gets gradually more and more sandy instead of gravelly. And then at the very top, we reach the mud, the very fine grained sediment. So by studying history in one single place, we can see how that place has changed over time. So we didn't move, but we went down deep into the sediment and found a place where there used to be ice, as recorded by that gravel. Then we were just offshore of the ice, as recorded by that sand. And then what we find in the most current position, modern seafloor, is the ocean sediments as the ice has pulled back. So that's one, but we did it a couple hundred times. And so we can reconstruct how the ice has changed over time in this area, giving us a better idea of what controls it. How fast can it retreat? How much has it changed over time? And the purpose of that is to understand how and why. We largely believe that what's driving the change in this ice is that warm ocean water is coming in, and that warm water is reaching the base of the ice. Anybody who can test this at home, and if you have ice in cold tap water, that ice might last for many, many hours. But if you put ice in warm water or hot water or boiling water, that ice will last for less and less and less time. And so if ocean currents are shifting and bringing more warm water into the base of the ice, then this ice is going to step back and back and back over time. And that's what we're trying to look at in the past. So we are stepping through, our colleagues on our cruises are doing things like studying seals to look at ocean temperature. We are also able to discover places where ice has stepped back and exposed islands that were not previously exposed. That was given a lot of attention. It's not that surprising though, as ice retreats. And our group has lots of interest in reaching students. This is one of our Instagram stories, just showing how cores are taken. So you can step through each of the physical, the logistical steps as those cores are collected. And all of these stories are posted for you to come in and see every type of work that we are doing. And with that, thank you. It's a beautiful place to work. And I think I speak for all of our team that we feel not only responsibility to get all of this story right for you, but great privilege to be able to go there and have this as our career. So I'm going to move to questions from Sarah when you're ready.
Great. Thank you, Julia. I might just, oh, you stopped sharing your screen. Okay, fantastic.
Was I supposed to?
No. I was just, you can keep it up there if you want, but might be nice just to see you. It's really good, really informative, I think. So thank you very much. So we will start, we have got some questions that have come in. We'll start with a couple of questions that actually came beforehand in registration, although I see that one of them from Jonathan Barker, he's also posted a question actually in the Q&A, and he is actually an ex-BAS radio comms person from King Edward Point in South Georgia from 1972 to 74. So welcome, thank you for joining us.
Yes, thank
He was asking on the coring, how do you establish a baseline for time? Or is it all relative over different levels and different types of deposits? So which part of the core shows where the original grounding line was?
So that is a fantastic question and should be easy to answer, but it's actually a really difficult task. So of course, one baseline is today, the modern surface in the ocean. And then the next thing that we would like to know is the exact place that it goes from being subglacial or sub-ice to being marine or subaqueous. So that line, I think, is what you're asking, where it goes from being under the ice to under the ocean. And you would think that would be easy, but it's not an exact thing that's easy to pick. One of our best tools is using the shear strength of the sediment. And actually, in one of the pictures I showed of the students in the lab, they were measuring shear strength. So we can test how tough the sediment is. And that helps us tell if it's been compacted and sheared underneath the ice versus just deposited in the ocean. So I think that was one of your questions, and that's one of the best tools. Fossils are the other way, where we go from marine fossils that are relatively pristine to any type of fossil, marine or past, older fossils that have been churned up and deformed under the ice. The third way, and it'll be the last example I give, is a pretty neat one. You can actually measure the pore water chemistry also. Pore water meaning the water that is between individual sand grains. This is another thing that was shown in one of those pictures. You saw those syringes trying to suck the water out of each of the pores. And those syringes are pulling water out from between the sand grains. Water that is deposited in the ocean will have sediment that is deposited in the ocean will have salt water in the pores. Ice is fresh water. There's no salt in the glaciers. And so sediment that is deposited underneath the ice has fresh water instead of salt water in the pores. That's all.
Great. Okay, I've got another one here, which is, what's the most unusual, surprising, or exciting thing you found when mapping the seafloor and taking samples?
Well, the most unusual thing, I think, because I'm not a biologist, I am often stunned by how much life we see. I didn't want to show you too many pictures because I'm here to talk about geology and the past conditions. But lots of times when we bring up our cores, there are brittle stars or worms or shrimp. There's a range of life just in every little, 3 or 4 inch bit we get of the seafloor. Sometimes we take videos of the seafloor. As we are taking our samples, we video the process underwater. And there are fish and octopus and things all the time, crabs sometimes, depending on where we are. And so I think our view of the barren, dark, deep ocean is really inaccurate. And as a geologist, I am most surprised by the biology.
Okay, what technological advancements have had the biggest impact on time? Do you think accuracy or capabilities?
The biggest technological impacts on our...
I read that incorrectly, sorry. So I think it's actually what technological advances have had the biggest impact on time, accuracy, or capabilities? So I guess in all the technological advancements, what has had the biggest impact on all your work that you're doing? How's it made it easier and things? Yeah.
So in many ways, being on an icebreaker and taking sediment cores is all pretty low-tech work. This is the same work we do today as in the 1970s, right? There's very little change to using a ship, breaking in, taking a sediment core, and bringing it back up. The higher tech things are in the lab analyses that we do afterwards. And so we are now able to do much finer scale reconstructions of time. You know, I didn't talk today about the fact that we do radiocarbon dating, we do lead-210 dating, so different chemical isotopes are used for dating, and we're able to get more accurate on smaller and smaller samples over time. We also do more and more types of geochemistry. We're not just looking at the sand versus the mud versus the gravel, right? That's a pretty simple way to look at it so that we can, you know, start to introduce the idea of sediment coring. But in reality, we are doing a great deal of lab work and geochemistry to work on those sediments there. And then I'd like to add one other thing that's really important, and that's satellite access to being able to work there. When we now have internet, not great, but at least sort of dial-up broadband level internet while we are working there. And there are satellites imaging the ice. And what that means is that with these almost daily new images of where the sea ice is, we are able to work in much more dangerous conditions than a ship would have been previously. Not that we are getting into danger, but that we are able to image the area with satellites and therefore know where we can go safely in ways that were not previously possible.
Great. So I've got somebody here who's actually with us from Sao Paulo in Brazil, which is fantastic. Great. So they are a researcher and would like to know what was the temperature of the cores recovered and how it was compared to the water right over it.
So the water right over it, of course, is above freezing. So let's say it's around 1 or 2 degrees. You know, the water is very cold, but it is not freezing. The sediment cores that we bring up are the same temperature as the water. So we don't typically measure the temperature of the cores. You know, we assume that they're around that temperature as they are brought up through the water column. But what we do is very quickly bring them inside the ship. We don't leave those sediment cores on the ship because we don't want them to freeze. If they freeze, it disturbs the sediments. You know, as the ice crystals grow, the sediment is disturbed and it disturbs the pore water chemistry that I just mentioned. So we really don't want them to freeze. And so we quickly bring them indoors as a way to keep them warm. We don't want them to freeze. If you drill deeper, another project I'm on actually 2 years ago, we got down about 800 meters. So much, much deeper down. That's deep enough so that we start getting the geothermal gradient and we find that the sediments are warmer and warmer as you go down, just like they are anywhere else on the planet.
I've got another question, anonymous person here who says, how windy does it get near Thwaites?
Sometimes really windy. So, you know, Antarctica is a windy continent. I don't know the details of wind speeds and times and records, but what I can tell you in a qualitative way is that it is cold and windy some of the time. This year, on this most recent cruise, we did have lots of days of wind and sea. There's no photos of those days because we're indoors, not doing anything. Lots of days where the wind was just great enough that we were unable to work, unable for the ship to hold position in one place, unable for the cranes to be used easily. So windy.
Okay. I've got a lady here, Coral, who's got a couple of questions about whether you've ever worked near Palmer Station, and in your cores, have you found dinosaur bones? And if not, if so, what kind?
Okay.
Sorry, so Julia, just to follow up with that, we have another boy, Ben, who's actually wondered whether you found woolly mammoth remains. So maybe that comes up with the dinosaur bones that you may find in your cores.
Okay, sure. Well, I'm going to try to go those in order. Yes, yeah. I've been to Palmer Station a few times. You know, one of my first slides, I showed my own personal cruise tracks. I've had 11 seasons, all in various parts of West Antarctica along the margin, and some of those have included Palmer. I really enjoy working near Palmer and in the peninsula. That's the prettiest part. You know, if you want to know the truth about working in Antarctica, it's if you just barely go down to Antarctica, just the northern part of the peninsula, close to South America, that's where you get the most scenery. If you go farther and farther south, it just gets colder and icier and darker. So I love working near Palmer. Have I ever found a dinosaur bone? No, but I have drilled into rocks of that age. So the best dinosaur bones in Antarctica, they're most famous anyway, are all exposed just across the peninsula from Palmer Station. So in the northwestern Weddell Sea, near Vega and Seymour Islands. And those are famous for dinosaur bone collecting. Again, so sort of across in the Weddell Sea. And we have drilled there and reached some pieces of rock that age. Unfortunately, when you're looking for dinosaur bones, usually you're not going to find them by drilling. Remember, when we're sediment coring or drilling, we get something on the order of 2 to 4 inches diameter back. So, you know, the best way to find something rare is not to push a straw into the ground and try to hope to get something rare. So the best way to get dinosaur bones are to work on land, and that's where they have been found in the Antarctic largely so far. I think Ben had the question about the woolly mammoths.
Yes.
To my knowledge, woolly mammoths only lived in the northern hemisphere. They are extinct now. They lived very recently, actually, and so that's something that I think is interesting to compare. Dinosaurs have been extinct for 65 million years, super long. So when we're talking about those fossils, we're going way back in time. They lived all over the planet. Woolly mammoths, to my knowledge, were only in the north. They could have been in the southern hemisphere, I don't know. But what I do know is that they've only been extinct on the order of 10,000 years. So they are a super, super recent phenomenon. And that is the age of the sediment that we're studying in Thwaites.
So I've got a couple of questions here who are sort of asking about what we can do to prevent climate change and to help sort of the melting glaciers of Thwaites. What can we help prevent it? And yeah, if you could answer that.
So that's an interesting question, and I'm glad you asked it because, you know, I don't want to leave any talk with just, oh, it's all melting and there's nothing you can do. So I'm glad you asked about it. On the other hand, it's a really hard question to answer and a difficult problem to address. Anybody can strive to reduce their carbon footprint. That is the most important thing on your individual basis, to reduce your personal carbon footprint, and whether that's to drive less or fly less, or turn the thermostat down in the winter or up higher in the summer, recycle your plastics, or even better, don't buy plastics. So those are all the personal things you can do. But to tell the truth, that's a tiny impact. It's a small impact that you can do on your own. And so I think the next step, the important step, is to help spread that word and to share it with your peers, your classmates, your students, your family, and multiply your impact into others. The truth is that even if we stopped inputting carbon into the atmosphere today, it's still going to take decades for the response to end. Mm-hmm. And so the last part is realize the change is already happening and make the adaptations as well.
And something that ties in with that, actually, we've got a lady, Lizzie, who's in Devon, who said that she's visited Antarctica as a tourist. So, but one of the spectacular sights that they enjoy is actually seeing the glacier calvings and the resulting icebergs. But as a scientist focusing on climate change, does that feel difficult and painful to see that? Different perspective, I guess.
Well, yeah, seeing glacier calving is one of the most exciting things. You know, I have some great videos where we've been lucky enough to see calvings up near Palmer Station that are just stunning. So I agree with you. It is really one of the most beautiful things you can see. It's also natural, right? I don't think that we should ever start to think that every calving is a sign of a problem. Calvings happen year round, season round, you know, in an ice age or out of an ice age. That is a natural process. Maybe they're happening a bit more sometimes, but we shouldn't look at every single one as automatically a sign of a problem. I think the question there, I think they were hinting at how do we feel about tourists going to Antarctica? And yes, there is a big carbon footprint for anybody going to Antarctica. The ship we work on, all of those days that we were there, we burn about 6,000 gallons of diesel a day. We have a carbon footprint just to make this study. Most of us think it's worth it so that we can understand it. I think you can make your tourism worth it as well. If you are lucky enough to get to see this, again, whether it's as a scientist or a technician or a ship driver or a cook or a tourist, whatever path you might be lucky enough to find it, I think it's still worth it if you go out and share it. You know, if you share that information, I don't begrudge anybody their tourism though.
So I have a question here from Camille. It says, what study path have you done today to do what you do today? And is it difficult to get a job to work for this kind of project in Antarctica?
So thank you for asking. I have 3 college degrees. So I did an undergraduate degree in geology, and then a master's degree in geology, and a PhD in geology and geophysics. Yes, it's difficult. Yes, you have to keep working and keep trying and keep studying. And the group gets smaller and smaller and smaller and smaller as you go up through those paths. But it's possible, you know, it's not in any way impossible. You just have to keep going and keep trying. And I would add to that, that our work, you know, I'm here as a scientist and telling you about the work that my colleagues and, you know, lots of students and I get to do there. And one of my favorite parts of the job is bringing students to Antarctica. You know, the fact that I get to bring young people with me and show them for the first time, that's really the best part of what we do. But there are so many other jobs there supporting this science, right? There are lots of people with bachelor's degrees in marine science or chemistry that are there as technicians, the boat drivers, everybody else that makes it possible. They all have different paths to that career. So lots of options.
And a bit of more of a personal question for you here. You've obviously clearly visited some most amazing parts, and what's been the highlight so far to you?
Well, this year is in some ways a highlight. This year, you know, was a very exciting cruise. We were interdisciplinary We had not just the geology, but the ocean science students as well, and the people studying the seals. And so I think that makes any cruise exciting, to be able to link different sciences together. 6 of us also got to go ashore onto that island I showed you and be able to, go there and name it. That's a very special feeling. It was able to make us really appreciate the fact that we were the first people there as the ice had pulled back. So I think this year is one of my tops.
Great. We're pretty close to our hour time, but I've got a couple more questions, which is good. Well, got lots more questions, but time for a few more questions. I've got another one here. Do you use submersibles to get footage of what's going on underneath the ice shelf? Which
some people do, yes. So I personally have not had the opportunity to do that science, but there are lots of colleagues that have, and there are a variety of ways. As part of the International Thwaites Glacier collaboration, there is a autonomous vehicle, an AUV, called the Hugin or RAN, that works underneath the ice as a small submersible autonomously. It's detached. In the peninsula, we've also had some that worked as tethered or cabled and take great footage of the seafloor. So there's a variety of ways. Yes.
Yeah.
One was lost last year.
And what I'm just going to actually add to that actually is we do have another talk this week about one of them is about robots in Antarctica, which would be mentioning the AUV that talked about. Okay, so let's have a look at that one here. Sorry, I've just got a couple of people who are wanting a sort of shout out. We've got a home educated family, Jiro and Koji from Wokingham in the United Kingdom. So welcome to them. And Gifford Middle School in Florida, which is very nice to have you here today. So another question here, where do you store the core sampling when you work on them, and how long do you store them for?
Okay, that's a good question. The cores are brought indoors, as I mentioned, so we don't let them freeze. And then we keep them between 2 and 4 degrees Celsius, so just above freezing, like a cold refrigerator temperature. After they are brought back on the ship to port, this year that was to Punta Arenas, Chile. Then the cores go to a repository, a place where they are stored long term. In the US, that repository is currently at Oregon State University in Corvallis, Oregon. And they're stored there indefinitely. There is so much time and money and effort and planning that goes into getting any of these cores that they are kept absolutely as long as possible. So, since the US Antarctic program has started, the cores are still there, 50 or 60 years later, indefinitely preserved.